All right, good day. And today, like I promised in class, I'm going to be showing you how to use some of this common software to interpret geoelectric data, resistivity data, and in this case, vertical electrical sounding data. And in the text that is accompanying this video, I have gone ahead to prove how you are going to use your various geometric factors for various arrays that you have, or electrode arrangements that you have for various resistivity survey. So first and foremost, we are going to be looking at this WINRESIST. First of all, let's open um, this test data, because that's the data we're going to be using today. Your typical data acquisition will follow this format. When you go to the field and use your meter, depending on the configuration of the meter, it will give you all these. But in our case, this data was actually acquired using a locally fabricated earth meter, and such it displays the V1, which is the potential difference 1 and 2, and we're going to get the final potential difference here, and it will display, the ammeter will display the current, which you will record, and we can now use it to calculate our resistance, so we are going to use this to derive our geometric factor based on what we have done in class, or using the accompanying text for this. So let's dive into it immediately. Like I said, we're going to be using WinResist, IPI2Win, and IX1D. These are very common, popular software that are used to interpret, analyze, and model resistivity sounding data. So typically, we have an arrangement like this, where you have your AB/2 from 1, 2, 3, 5. At the 6, 6, you change the electropotential distance. I'm sure you know how to do this, but let's just dive into, because from this, that's when we have to go to using the WinResist. So in calculating your dV, it will be equal to the absolute value of this minus this. That's the way to find the dV, and this give you this data. If you click on this cross here, it will autofill the ones that are down here. That's the idea. So this is for this cell E2 rather, you have absolute value of this and this, which is this 2578. Same thing applies here, same thing applies here. This just makes it faster. Excel makes it faster to calculate some of these numeric values. Okay, in getting our R, it is dV over I, which is equal to E2 divided by F2, will give us our R, our resistance. This is E3 divided by F3 and go. I have done this before, so that's why the formula computed automatically. Then to find the G, or geometric factor, this now will be equal to, we have our pi, which is 3.142. This is the formula to calculate the geometric factor. Let me pause this video and show you okay, actually this is the formula that we use to calculate our geometric. Like I said, it can be K or G depending on the text you are using. So it's actually pi multiplied by AB/2 squared minus MN/2 squared all over 2 MN/2. So let's put it in the formula bar of Excel. So we have pi, so we open brackets. Okay, we have pi, open brackets. We have Mn over AB/2 squared. So AB/2 squared, we use this shift 6 carat AB/2 squared. That's what we have there. we'll put this in brackets too, AB over 2 squared, and this will be minus Mn over 2 squared. Mn over 2 is V2, and we'll put this in brackets too, just to simplify our formula. Mn over 2 squared. Okay, we enclose all this in a bracket, divided by 2 times Mn over 2, divided by, let's put this into bracket again, 2 multiplied by Mn over 2, going by this formula that we have here, 2 by Mn over 2. So that's what we have. So if you click on enter, yes, let's accept this. So it gives the G here is 2.365. Automatically calculates for the rho, because rho is, that is the resistivity, is G multiplied by R, which is H2 multiplied by this. So if we click on this cross here, all these values appears here. So we now have our Mn over 2, AB over 2, Mn over 2, our G, and our rho. These are the very important things that we actually need to go ahead and use WINRESIST. So when we open WINRESIST, so what we're going to do is just shift this here for format purposes so that we will see exactly what we are working on. Just shift it to this side. This accompanying graph, you shift it to this side. So it said, welcome to WINRESIST version 1.0, and all this information. Press any key to continue. Can press any key to continue. For me, I press S, which will be for Schlumberger array. All these highlighted in green here are the keys that you're going to press for it to activate the particular array that you need. In this case, we are using Schlumberger array, so we are activating Schlumberger array. So you hit the enter key. Now these things appearing on green here, anytime you press the accompanying letter, it displays whatever you need. And in this case, we are going to start with entering field data. So we press E to enter field data and press enter. Now it's telling us what is AB over 2. In this case here, we have AB over 2 as 1. Click enter. And what's the resistivity? We have it as 225.83. 225.83. Click on enter. So you click continue entering all these values. We have press 2. The AB over the resistivity is 202.78. We have 3, and the resistivity is 124.01 or 02. We have 5, and it is 120.6667 in this case. And we have 6, and the first 6 is 135.67 or 68 in this case. Now if you click enter, you know we are repeating 6 here. So what you are going to do is to change the electrode potential distance, that is the Mn distance, by clicking on C. Now you see automatically it's replacing that 6 because we are changing the electrode potential distance here, and the resistivity for the other 6 here is 115.08. 115.08. Click enter. So you continue entering this data. So I'll pause the video while I finish entering that video. But let me just show you something again. We have 8. AB over 2 is 8, and the value is 152.8. 152.8. We have the first 10, and the value is 225.11. 225.11. So what you are going to do now, since we are repeating 10, we are changing the electrode potential distance, you just press on C. So 10 appears automatically while you enter the value of the next 10, which is 228.05. 228.05. So now would be a good time to pause the video while I finish entering the data. We'll come back to rate. So we're back. So when you have finished entering all this data, the next thing for you to do, it will ask you, do you want to quit the procedure? Or if you have made a mistake in the next segment, for example, if you have made a mistake in this 100, we'll not go into that right now. All we want to do is to make sure that our data is entered correctly. So you will press Q to quit the procedure. Press Q to quit the procedure. So what happens now is that it will ask you press any key to continue, because it's displaying all that you have entered. We press any key to continue. It's asking, are there typing errors? And the answer is no, we don't have any typing errors. We press N, that we don't have any typing error. So when you press N, it displays that for you here. It displays the plots, the points on this particular graph. It is important to know that you can use U to actually take this thing down. U takes it down and D takes it up too. So if you press U, you'll be able to see how the data is like. So you continue. Once you are here, you press C to continue. So do you want to save the rough data? If you like, yes, I will click on yes. What is the name of the data? We'll say tests. That is the name that we want to give to it. What give the location of the VES sounding? We'll say FUTMX. So you press enter. Now that we have done it, the next thing for us to do is to model. Just before we do that, let us come down here and look at this Excel. First of all, what I do is that I plot this particular data manually, so it gives me a sense of the model parameters that I'm going to be choosing. So I'm plotting AB over 2 against row here. So what I'm going to do is to insert a chart for here. This actually gives you a bar, but you know that the chart, this plot has to be in double logarithm format. So I'll go to format axis and choose logarithm scale. Same thing will be applied here. We choose logarithm scale. Now we have it. Don't mind this particular sharp bend here. It's just indicating where you have these repeated values. If you don't want to see these sharp bends here, all you need to do is to find the average of both of these, which will give you a smoother curve. But then that is not the problem. Remember, I said when you start having inflections, that's when you propose to have a particular layer, you know. So if we look at this, we'll see that at this particular place we have an inflection. When we get here, although here we have an inflection but it's a little bit muted, we have another inflection here. And like we said in class, somehow this particular point may likely be an outlier or a noise somehow that may be not a very real data, that may be caused by instrument noise or something, but then it can still be real data. So we don't do much about this. We leave it as it is and see how we can manipulate our data. So in my case, if I look at this thing very well, it looks much like a 3-layer kind of curve, a 3-layer type curve. So where I see my inflection, I go with it. So like here, you see if you click on this place and hover your cursor around it, it said this point is 0.2, we are 2 meters, and the value of the resistivity is this. So but the inflection is happening between this place and this place. So and this is 3 meters. So I will assume that my inflection is happening at between 2 and 3 meters. And if we find the average between 2 and 3 meters, we are likely seeing like a 2.5 meter point. So once it is 2.5, remember when you want to model the AB over 2 distance that you are seeing here, you divide it by 2 to give you the depth that you are going to choose as your model. So in this place we have the first layer. Okay, let's just name it something like, we have depth, and we have resistivity here. So depth, we say, is between this place and this place, and that is 2.5. So half of 2.5 is actually 1.25. So let's go with like 1.5. And the resistivity between this place and this place, if this is 124 and this is actually 202, we're having like 326, 150, 160 thereabout. So the resistivity should be about 160 ohms. That's for the first layer. So let's continue. When we see another inflection here, we see another inflection point around here, thereabout, because as this one is coming, something is rising around here. So if we choose this point is 0.6, and it's coming to this place, which is 0.8. So we assume that it is happening, the inflection is happening between 6 and 8, and that's, if we find the average of that, we have about 7 meters that this thing is occurring. So 7 meters divided by 2 is 3.5 meters. So, and we'll look at the resistivity where it's happening. The resistivity for this is 152, and for this place is 135. Okay, 115, 152, 260, so about 130. So we give it a resistivity of 130. For 3-layer curves, we know that the depth for the final layer is always at infinity. So we choose the last resistivity here, which is 1250 approximately, to be our final. So this is the model, the first starting model that we're going to impute to give WinResist a particular model that it will use. So let's come back to this place and click on this one. So here we are going to do model entry. So you click on M, and it's asking us total number of layers. We say we want it to be 3, and it's asking us, you want to work with thickness or depth values? I want to work with depth values. So I click on D and it gets me here. So it's asking me, what is the layer resistivity for first layer? Layer resistivity here, we said it's 160. Here, let's remember this is 160. And the depth at which it's occurring is 1.5 meters. And the layer resistivity for number 2 is 130. And it's happening at 3.5 meters. And the final layer resistivity is 1250. So here we have it. So it's not that you have to correct in resistivity. If you have a correction for the resistivity, you can press R. If you have correction for the depth, you can press D. If you have correction for the number of layers, you can press N. But in this case, we do not have any of such. So we'll press C to continue. Now it's continuing. So it has plotted something like this. Like you said, like this is the layer that we have chosen, and this is how it roughly interprets. But we know that because this is a software, we are going to do an iteration on this particular first layer that we have offered. Iteration means that it tries to balance balance the synthetic data that has been produced for a particular layer like this and this data that we are offering. So the difference between the mismatch between the synthetic data that has been inbuilt into the system and the data that we have supplied will give us the RMS error. We also know that this synthetic layer have been modeled against those master curves that we talked about, the Orellana and Mooney master curves. But because of time factor, we're not going to go into details here. It will suffice it to say that we have given our first model. The next thing for us to do is to do our iteration. So, but we'll click on C to continue here. So the next thing for us to do is to do iteration, see I. Once we click on I or press I, it will take us to iteration. So if we continue pressing C, this data will continue to be iterated. As you can see, it's trying to match the thing accordingly. So if we continue to press C, you see it's trying to fix this line, this smooth curve over our data. You can display the error by pressing E, and we have an RMS error of 6.33, which is okay, but not too okay. So we can continue our iteration process by pressing C. You have a maximum number of 30 iterations, but we're at the 4th iteration, so you can continue pressing C while it continues to refine. As it were now, our error may not be reducing, because if you press E and see the error is at 5.26, it's not reducing. Let's continue. Let's do 15 iterations, and let's check the error. You see 5.25, it's not having much effect. So at this stage, you can either stop or continue up to the last iteration. Most times it doesn't matter. So but let us go all the way and get to the 30th iteration, which the software has permitted. Now, so the next thing for us to do is, after we have done this iteration and we are satisfied with the result that we have got, all we need to do is to screen display by pressing by pressing S to screen display. So location, we said it is FUTMX. So this is how it has appeared. Now let us look at it. We actually provided these model parameters that at the first layer depth it's 1.5. When we finish our iteration, it came down to about 1.2. Our second depth that we offered was 3.5. After its iteration, we got to about 3.9, and we said that the resistivity for this is 160. The iteration took it up to 254 and 161.8 thereabout. So that is the essence of using this software for this iteration, because it uses some mathematical formula to actually make this process a lot faster, instead of using those master curves and doing manual curve matching. So this particular thing, so we have made an attempt to reduce the ambiguity, or rather we supplied a close enough information for this iteration to take place. So we have got something that is nice. RMS error of 5.2 is not bad, especially when you consider the fact that this data was acquired using a locally made thermometer. So how do you now display your results? All you need to do, if you have this sniping tool, all you can do is to open up this sniping tool and snipe this and save it somewhere of your choice. So you can do file and save as maybe something PNG. Okay, so we can now say this is tests PNG. Okay, so we have that saved, so we can always call it up anytime we like. So that ends it for Slumberger, but we'll keep this and now try another software, which is IPI to win. So in order not to make this video too long, I will stop here and do that of IPI to win and Interpex IX1D, and we'll see how the results compare to each other. But the bottom line is we have been able to do these things using Excel. We plotted it using Excel, made our first model, we gave our model parameters using Excel, use this software to actually iterate over the model that we have offered, and we got a reasonably good result here. So that ends this particular tutorial. I hope you find it useful. If you have any challenge, you can call me or email me whatsoever. I'm ready to answer your questions. There are still a lot of things that may be needed to do in this thing, especially when you have made some errors, how you're going to fix it. Even if you want an RMS of 2.5, how you're going to do that. But that's beyond the scope of what this lesson is going to teach you. But this is just a basic introduction and a basic interpretation skill that you need to acquire to actually interpret resistivity sounding data. Thank you very much. God bless you.